Then in double integral, right, f of xy dx dy, where x goes from a to b and y goes from c to d, well, f of xy, right, this is y is equal to f of x, right? This is the y-axis. So C and D, and here we have A and B on the x-axis. So we are integrating some function defined in two variables, z is equal to f of x, y, over the rectangular region in the xy plane, sorry, above the rectangular region in the xy plane, or as a matter of fact, as we saw later on, it didn't have to be a rectangular region, right? It could have been, so let's say that this is z is equal to f of x, y, right? It's going to be a three-dimensional surface. So this gives you the volume below the volume of this, right, under this sphere and above the rectangular region, or any region in the xy plane. Okay, and then we move on to the triple integral. And the question is, well, what is going to happen now? So now if I evaluate the triple integral of a function defined in x, y, z, dz, dy, dx, first of all, what does this represent? Okay. The first thing that we have to think about is that this here is a four-dimensional surface, right? So I have a certain function, let's say w is equal to f of x, y, z, right? So I have three variables, and then the output is going to be in one dimension. So that's one dimension plus three, that's four-dimensional object. Okay. So I'm sorry. Single integral function in one variable. Okay. I'm integrating on the interval from a to b. I split the interval onto n subintervals. I add them up and approximate the area under the curve, send the limit to infinity, and I defined the interval. Okay? In the double integral, right? How did we do this? I split the interval from a to b onto n subintervals, and I split the interval from c to d on the y-axis onto m subintervals. Okay? That gives me n times n squares into the xy plane, above which I integrate the function, right? This is the height. This is the height of each box here. I have double Riemann sum. I send n and I send m to infinity, which leads me to the definition of the double integral. And then the triple integral. I have four-dimensional object that I'm not even going to try to imagine it, and obviously not try to sketch it. But what I can sketch the region, if you want, or the object, or the solid, above which I integrate this four-dimensional object. Okay, so obviously I'm not going to subdivide an interval. I'm not going to subdivide a region. I'm going to subdivide a three-dimensional region. Okay, and then I'm sorry for this, but it is easier for me just to show you the picture in the book, right? It's right here. Okay, so now the function depends on the z, the x, and the y values. Okay, so I'm integrating above this region right here. It's three-dimensional. So I divide x, the interval x AB onto n subintervals. I divide the interval y from C to D onto m subintervals, and I divide the interval from R to S on the z-axis, right, onto L subintervals. Okay. Each of them gives me what? This doesn't give me a mesh, but it gives me a sum of cubes. Each cube has a volume. That volume is defined by delta y times delta x times delta z, right? And then if I want to integrate this function right here, so this is going to be what? This is going to be a value in the fourth dimension, a function that depends in three dimension, f of x, y, z, right? So that's the height in four dimension. For each point in each cube right here, times delta v. Delta v stands for the, whoa, I really cannot sketch with this. Delta v stands for the the volume of each subcube right here. Okay, and this is the definition. This is the definition of the triple integral. The triple integral is nothing else but the triple Riemann sum as L, M, and N go to infinity. Okay, if we subdivide the interval A, B, C, D, and RS into M, N, and L subintervals respectively, and then just send all of those to infinity, then I'm just going to get the definition. I'm going to get the definition for the triple integral. Okay, and then if we look at the Frobenius theorem of triple integral, this is nothing else but it leads us to the iterated integral, right? Where the triple integral of the function defined in x, y, and z over dv is just evaluated in such a way that when I integrate with respect to x, I treat y and z as constants. When I integrate with respect to y, I treat x and z as constants. And when I integrate with respect to z, I treat x and y as constants, okay? So let's do a very, very simple question here. Let's choose one from the book, something extremely easy, just to show you how these integrals work. I want even something easier than this. Okay, here we go, example. Evaluate the triple integral of x, y plus z squared dv above the region defined, so I'm doing question number 2. Okay, above the region defined as all the points x, y, z such that x is between 0 and 2, y is between 0 and 1, and z is between 0 and 3. And it says using 3 different orders of integration. Well, there are going to be 6 different orders of integration here, and we're going to talk about that in a second, and we'll just do this with 2 different, okay, because it's an easy example. So let's say first case, I'm going to evaluate x, y plus z squared. Doesn't really matter. Let's say dx, dz, dy. Okay. For no particular reason, chose this order, okay? So that means that x goes from 0 to 2, from 0 to 2. Z goes from 0 to 3. Okay, and the last one, y goes from 0 to 1. Okay, so first I integrate with respect to x, right? Means I treat y and z squared as constants. So the double integral from 0 to 1, 0 to 3. Integral of x is x squared over 2 times y, where x goes from 0 to 2, minus z squared times x evaluated from 0 to 2. And then I'm left with dz, then dy.
Ivo, it's plus.
Plus.
Yeah.
Thank you. And then solve this. That's 4 over 2 is 2, right? When you plug 2, 2 squared is 4 over 2 is 2, so 2y. 0 over 2 is 0 times y is 0. Plus, plug 2 for x, plus 2z squared dz dy, which is equal to the single integral of, so I'm evaluating this with respect to z, I'm evaluating this integral with respect to z, that's 2y times z plus 2 over 3 z cubed. Z goes from 0 to 3, dy, which gives me the integral 3 times 2 is 6y, plus 3 cubed is 27. 27 divided by 3 is 9 times 2, 18, plus 18 dy. Right? When you plug 0, everything just becomes 0 because I have z here and z here. And finally, this is 6 over 2y squared plus 18y, and then y goes from 0 to 1. So this is 6 over 2 plus 18, and that's equal to 21. Okay? Now, of course, you can, the Fubini theorem works for any multiple integral, so it's going to work with this one. As I said, there are 5 different orders, right? When you keep x here, these two can change, that's 2. When you keep z, 2, x and y can change, so that's 4. And then when you keep y at the beginning, x and z can change at the end, so that's plus 2, that's 6 different ways to integrate, to evaluate, to set up a triple integral. Okay, now this is very simple. I don't even know if I should bother you with this because this question is extremely easy. I don't know, let's change the order. Y, x, z, I don't know, dy, dx, dz. So I'm doing the same problem. Here I have x, y plus z squared. And unless I made, or I'm going to make a mistake, this should have absolutely the same answer. So y goes from 0 to 1. X, the second one is from 0 to 2, and the third one is that from 0 to 3. So let's speed up on this one a little bit. 0, 0, 3, 2. I integrate with respect to y first, x over 2 y squared plus z squared y, evaluated from 0 to 1, dx, dz, which is equal to the double integral. Now I'm about, this is y, right? So when y is 1, I just have x over 2 plus z squared, and then you plug 0, everything becomes 0. Now I integrate with respect to x. That's x squared over 2 times 2, right? Plus z squared times x, evaluated from 0 to 2, dz. That's the integral from plug here 2. 2 squared is 4 divided by 4 is 1 plus 2z squared. And then you plug 0 and everything. This function here evaluated for x is equal to 0 just vanishes. dz And now you integrate with respect to z, you get z plus 2 over 3 z cubed, evaluated from 0 to 3 is equal to 3 plus 2 over 3 times 27. This is 9 times 2 is 18 plus 3 is 21. Okay, so the triple integral, where the bounds are just rectangular regions, is as easy as the double integrals evaluated in over rectangular regions, right? Where the problem starts. If there are any questions about this, please ask me and I'll come back. The interesting, which means slightly more complicated thing, begins when we integrate over general regions, right? So okay, so there are a few cases that you have to, well, cases that we have to think about. So let's say that we have a solid of the following type. Okay, and then we evaluate this over x, y, and z. Okay, so look at this. This right here on top, okay, this sphere on top, okay, this solid is going to be what? Well, this is some function z1, which is f1 defined in x and y. And this one, on the other hand, or let's say z2, doesn't matter, is z2, just this part right here, which is some other function defined in terms of x and y. Okay? So bounding this is going to be interesting, because now z is not going to go from constant a to constant b like in the previous case, right? Now the value for z is bounded between, this is 1, f1 defined in x and y, and then f2 defined in x and y. Okay, and this has to be the first integral that you're going to evaluate, right? So you're going to start with this integral. So the integral, right, over f of x, y, z dv over the region E in 3 dimensions, it is going to be evaluated as the first integral that you're going to define is going to be z. So you're going to first integrate with respect to z. Okay, and that's bounded between f of 1 and f of 2 in terms of x and y. Maybe this is wrong choice of letters. So let's say here I'm integrating the function h of x, y, z. Okay. But then what happens? Excuse me. This is going to result into some function. This integral is going to result into some function. And we are left with what? We are left with double integral, right? And we already know how to evaluate this. When I'm evaluating double integral, I have to evaluate it over the area that's dropped on what? Well, if I'm done with the z value, then I'm left with this projection, this shadow of the solid into the xy plane. And this is what? An integration over a general region in 2 dimensions, in x and y. Okay? Well, here it's up to you how you're going to set up this, whether you're going to say y is between some function g1 of x and below g2 in terms of x, and then x is going to be bounded between a and b, and then x is going to be bounded between a and b. So finally, this triple integral is going to be dx going from a to b. Okay. The second one is dy. Y is bounded between g1 of x, g2 of x, and dz is bounded between f1 and f of 2, both of them in terms of x and y, and you're integrating the function h. Okay. Of course, somebody can say, well, can this first, so basically here I have two possibilities, right? Maybe you can say, okay, what if I say that x goes between omega of y and omega 1 of y and omega 2 of y. That's absolutely okay. And then y is going to be between c and d. It's going, actually, this is a question up to you, for you to find. This is the point C, and this point here is, this is the point C. It's up to you to find the most optimal or the only possible way to evaluate this triple integral. Okay. So, are there any questions so far? Let me see whether this GeoGebra is going to work. And while I do that, there it is. Okay, so what did we say? For a single, for a double integral, you can find an area of the region by evaluating 1 dA over some region D. Okay. The same way, you can find volume of a solid. You can find a volume of a solid E, or a three-dimensional object E, when you integrate 1 over dV. Sorry, dV over E, because E is three-dimensional region. Okay. So let's say, as a first example, find the volume of the region E enclosed by the surface z is equal to x squared plus y squared, and z is equal to 8 minus x squared minus y squared. Okay, so here you should be able to recognize these two surfaces, right? This is just going to be intersection of two paraboloids. Okay, and that is going to look like something just happened. Do you zoom out here? Okay, so Okay, so there you go. This is what the region, the intersection is going to look like. Okay, so this is x squared plus y squared. Okay, paraboloid open upwards towards the z axis, and then 4 minus x squared minus y squared. Actually, ours is 8. Let me see if I can change this. If I can change this function, aha, that's what's going to happen. And now my problem is that I don't know how to zoom out here in order to see how this is going to look. So it's going to be similar to the one that, let's say, 3. So, oops. It should be, so this is going to be the form, but it's not going to cut it across the z-axis at 3, but at 8. So the idea is the same. Okay. So how am I going to find the volume of this solid obtained by the intersection of these two surfaces? Okay. Well, by definition, it's right here, right? The volume of this three-dimensional region is the triple integral of 1 over that region. So let's find the bounds of that region. Okay. So one way to do this, and most probably the easiest way, is to start by bounding the z value. So that means for any xy, right? Let's say for this xy, this point right here, what is going to be, from where to where is going to be go the z value? So it's going to start with the paraboloid x plus y squared, x squared plus y squared is going to go to its upper bound is going to be the inverted paraboloid, 8 minus x squared minus y squared. Okay. So z is going to be between above x squared plus y squared and below 8 minus x squared minus y squared. Okay, so I'm done with the z value. So this is going to be the double integral of the integral dz, where z starts from x squared plus y squared and finishes with 8 minus x squared minus y squared. And now, so let's say, of course, you don't have to do this. I'm just explaining this at the beginning. You don't have to do this step. And then I have a double integral over the region D. And what is going to be the region D? Well, in a way, if you want to talk about it, it's going to be the shadow casted upon the xy plane, this circle right here, right? So how are we going to find that? Well, that's going to be the intersection. That's going to be the intersection of these two paraboloids projected onto the xy plane. So now I need to find the intersection, but the intersection is very simple, right? So from here, the intersection of these two paraboloids is z is equal to x squared plus y squared is equal to z, 8 minus x squared minus y squared. Okay, so what do I have here? I have 2x squared plus 2y squared is equal to 8, right? So what do we get? We just get a circle with radius 2. So 2x squared, 2y squared is equal to 8. Again, how did I get this? By putting these two equal to each other. And I get a circle with radius 2. So now be careful. We're dealing with Cartesian coordinates so far. So far I'm doing this only with Cartesian coordinates. What is this? This is the projection of the intersection of these two curves on the xy plane. And that's what we did, right? When we talked about triple integral over general regions, you bound z, right? And then you deal with the double integral that's left by looking at the projection of this intersection onto the xy plane. And that's exactly what's happening here, right? So I found the intersection here, that it's not, you can see the intersection right here, this circle, right? And then projected over the xy plane is going to be the circle crossing through 2. Now, why it doesn't cross through 2 here is because this function here, I can just sketch 3 minus x squared minus y squared for the reasons that I already said, that I don't know how to zoom out this picture here that I found it online. Okay, so now it's up to you. It's a circle, so you can bound it any way you want. So let's say y is bounded between square root of 4 minus x squared and minus square root of 4 minus x squared, right? So y goes from here, from this graph to this graph, right? Maybe another color would be more appropriate. To this here. So y goes from here to here. Okay, and finally x is from -2 to 2. Okay, so this triple integral finally is going to be, well, x goes from -2 to 2, y goes from negative square root of 4 minus x squared to square root of 4 minus x squared, z goes from x squared plus y squared to 8 minus x squared minus y squared. dz, first I'm integrating with respect to z, then with respect to y, then with respect to x. Of course, if you decided here to bound x first, then this order here would have changed. Okay, and now let us just solve this integral that, although it may look naive at the beginning, very soon we'll see that it's not as naive, or maybe it is, I don't know. So first integrate with respect to z. Integral of 1 is just z. So I have the double integral from -2 to 2 and from negative square root of 4 minus x squared to square root of 4 minus x squared times z, which is a value from x squared plus y squared all the way to 8 minus x squared minus y squared dy dx. Okay, so if you guys want, and if you're not already doing that, please evaluate this integral with me simultaneously and check my lines. Okay, plug this function instead of z and this function instead of z. So that's 8 minus x squared minus y squared minus x squared plus y squared dy dx. So from -2 to 2, the integral from negative square root of 4 minus x squared to square root of 4 minus x squared. I have 8 minus 2 x squared minus 2y squared when you drop this parenthesis, right? dy dx. Okay, one way we can help ourselves is to factor out constant 2 for each of these terms here. And now this whole expression here doesn't depend on y, so treat the whole thing as a constant, taking into account that I've already factored the 2. So that's 4 minus x squared minus y squared. And now I integrate it with respect to y. I can use one more line here. That's 2, negative 2 to 2. This is 4 minus x squared times y minus 1/3 y cubed. And now y runs from negative square root of 4 minus x squared to square root of 4 minus x squared, and finally dx. Okay. So let's plug these expressions for y. That's 2 times the integral from negative 2 to 2, 4 minus x squared, square root of 4 minus x squared. And then I can plug this one here, minus square root of 4 minus x squared. Right? So I plug this expression and this expression for this y first. Minus 1/3 square root of 4 minus x squared cubed minus negative square root of 4 minus x squared cubed dx. So let's see what we have. At this point, this 2 minuses cancel and I get 2 square root of 4 minus x squared. Negative 1 to power 3 is negative 1, right? So minus and minus, they don't cancel here, which I don't know which one is better. So I get 2 times square root of 4 minus x squared cubed. This is equal to 2 times the integral from negative 2 to 2, 4 minus x squared times 2 square root of 4 minus x squared minus 2 over 3 square root of 4 minus x squared to the power of 3 dx. Okay, any questions? Okay, so let's do a few things here. First of all, this is to power 1, right? 4 minus x squared to power 1 and 4 minus x squared to power 1/2. So just remember that a to power 1 times a to power 1/2 is equal to a to power 3 over 2, which is exactly this expression. Okay, so this is nothing else but 4 minus x squared to the power of 3 over 2, which is square root of 4 minus x squared cubed. Okay, so that's 2 times the integral from negative 2 to 2, 2 times square root of 4 minus x squared cubed minus 2 over 3 square root of 4 minus x squared cubed dx, which is equal to 2 times the integral of 2 minus 2 over 3 is 6 minus 2, 4 over 3 times 4 over 3, right? 6 minus 2 is 4 over 3 square root of 4 minus x squared cubed dx from negative 2 to 2. Okay, smart guys, and even more important, smart girls. I'm sorry, I have to improve my language. I say guys when I mean everybody else. How am I going to evaluate this interval? Eric, I can't stop thinking about you, buddy. You're my Cal 2 student, or maybe not, maybe Cal 1. Anyhow, give me some. So yes, Eric, you turned your mic on. Let's
Hello,
go.
does it work?
The floor is yours.
I'm doing it as fast as I can, but you're way faster, Evo.
Okay, look at this integral. Do you have any ideas how to solve it?
That one there. Bring the exponent of the.
No, stop. Anybody else?
Trig sub.
Trig sub, trigonometric substitution, okay? So just when you thought that you're done, it's one of the ugliest, well, ugliest. It's not such a cute integral, so x is equal to 2 times sine theta, dx is equal to 2 times cosine theta, d theta, right? So this becomes 8/3 times the integral of 4 minus 4 sine squared cubed times dx is 2 cosine theta d theta. When x is -2, I have -2 divided by 2 is -1. Arcsine of -1 is -pi/2. When x is 2, 2 divided by 2 is 1. Arcsine of 1 is pi/2. Okay. We move on. This is 8/3 times the integral from -pi/2 to pi/2. Factor 4. Square root of 4 is 2. Cosine theta d theta. Okay. So, and this is to the power of 4. That's pretty, sorry, to the power of 3. That's pretty important. Okay. So square root of 2 of 4 is 2. 2 cubed is 8. If Eric thinks that I'm going too fast, maybe I should slow down a little bit, but I think I'm going pretty slow. So that's square root of 4 to the power of 3, then square root of 1 minus sine square theta to the power of 3 times 2 cosine theta d theta. Okay, and at this point, this is 8, and this is 2. So 8 times 8 is 64, times 2, 128. 128/3. So 8 times 8, 64, times 2, 128. Times the integral of 1 minus sine squared is cosine squared, square root of cosine squared, so only this here is cosine squared. Square root of cosine squared is cosine, cosine cubed times cosine theta d theta. And what do we have? We have a trigonometric integral cosine to the power of 4 theta d theta. And again, if you have forgotten how to evaluate this, well, you go through the double angle formula. That's cosine square theta squared d theta, which is 1/2 1 plus cosine of 2 theta squared d theta, which is equal to 128/3 times 1/4. That 1/4 is right here, right? So 1/2 squared is 1/4 times the integral of 1 plus 2 times cosine of 2 theta plus cosine squared of 2 theta d theta. Almost there, guys, almost there. Now we build this number up 128. Now we start canceling it down. Okay, that's 32 over 3, 128 divided by 4 is 32, times integral of 1 theta, integral of 2 times cosine of 2 theta is 2 times sine of 2 theta over 2, evaluated from negative pi over 2 to pi over 2, plus this integral right here. But that integral again is going to be evaluated by the double angle formula, which is 1/2 1 plus cosine of double this angle, cosine of 4 theta d theta, evaluated from negative pi over 2 to pi over 2. So that's equal to 32 over 2, plug pi over 2, 4
That's
theta,
32 over 3.
thank you, minus negative pi over 2, right? Plus, these two are gone, okay? Sine of 2 times pi over 2 is sine of pi 0. Sine of 2 times negative pi over 2 is sine of negative pi, which is 0. So 0 minus 0 is 0. Okay? Plus 1/2 times integral of 1 is theta plus sine of 4 theta over 4, evaluated from negative pi over 2 to pi over 2. This is 8. Oh my God, this refuses to stop this problem. Okay, so this is 32 over 2, sorry, over 3. Pi over 2 minus negative pi over 2, that's pi over 2 plus pi over 2, that's pi, plus 1/2 pi over 2 minus negative pi over 2, plus, and again, sine of 4 times pi over 2 is sine of 2 pi, sine of 2 pi is 0, minus sine of negative 2 pi, that's also 0. 32 over 2 pi plus 1/2 pi over 2 minus negative pi over 2 is simply pi. Wow. Okay, we're done, right? And this is 3, sorry. So that's 32 over 3 times 3 pi over 2. Cancel everything and you get 16 pi. Oh, that was quite a lot. Any questions?
I have a question.
Uh-huh.
Instead of doing it like in X and Y, could we have not done it in like cylindrical coordinates?
Of course, absolutely. I just wanted to show you that if you don't choose the right method, you're gonna suffer. You're gonna get the right answer, but you're gonna suffer. So yeah, cylindrical coordinates come into mind, where this here, so Z is going to stay between r squared and 8 minus r squared, right?
Yeah.
But then r is gonna go from 0 to 2 and theta is gonna go from 0 to 2 pi. Well, now that triple integral is way easier, right? No square roots involved here. Theta doesn't depend on r. So right away you can pull out the 2 theta out. But we have to wait a little bit because we're going to learn tomorrow or on Friday about the cylindrical coordinates. When you do a triple integral in cylindrical coordinates, similarly, like polar coordinates, integral in polar coordinates, that r is going to appear. So that's the only thing that you have to be careful about. But your intuition is spot on.
And I haven't, well, are we going to learn like, is it possible to do like triple integrals in like spherical coordinates with like phi and stuff?
Yeah, that's what that's why we learned those. We are doing that on Friday. First cylindrical coordinates and then spherical coordinates on Monday. and we're done with the material.
Oh wow, okay. Great, thanks.
No problem. Okay, so that is that. And this is question 9. Okay. So let's see my notes. As you can see, guys, here you do one mistake, right? It's very difficult to find your mistake, right? So just imagine your webwork assignment when something is not going to be right. I'll go and figure out your mistake, right? Example 2. So express the integral of the function f defined in x, y, and z over the 3-dimensional region E, okay, where E is the region in the first octant above the plane y is equal to z and bounded by the cylinder x squared plus y squared, plus z squared is equal to 1. Okay, so here it doesn't ask us to solve. Well, I don't even know what the function here is. They ask us just to set up the triple integral. Okay, so to find the bounds of x, y, and z. Okay, in order to do that, I have to sketch this situation as good as I can. Okay, maybe it's not going to be that easy. So first of all, let's start with the cylinder here. So I have a cylinder x squared plus z squared is equal to 1. That means it's just going to be the cylinder right here, right? For any value y. And now we're doing this only in the first octant, okay? So let's do that first. So I have something like this. So it's just this part right here. So it's bounded by these planes, right? And then we cut through it with the plane z is equal to y. So z is equal to y is going to be this here plane. Okay, so this is the plane y is equal to z. So once I have this preliminary idea of what this is going to look, I can sketch it in a slightly, let's just zoom in. Okay, so what do I have? I have the cylinder here, right? It's going to be a quarter of a circle. Okay, and then I have this plane that cuts through it, right? So basically, this is going to be my region above which above which I integrate the function f of x, y, z. Do you understand this? Should I do this again, or you have some kind of understanding of what's going on?
That's good.
Okay, so now it is your choice how to start, right? Anything works by the Frobenius theorem. The question is, which is going to be the easiest or, right, the most economical, let's say. At certain point, your choice is affected by the double integral, which means by that projection, by that shadow in the 2 dimensions. If I bound z, which I can, it is going to be above y and below square root of 1 minus x squared. The problem with that is that this here slice, I'll have to project it into the xy plane. Okay, which, to be honest, is not that difficult. It's not a problem. But something easier is to project this equation of the unit circle into the xz plane and to deal with that. In which case, I have to start by bounding what? By bounding the y value. So basically, I want to express this integral as integral of f x, y, z dy, and then I'm going to choose dA, and here it's going something like this. That's my idea, okay, over the region D. Okay, and the region D is going to be what? In the xz plane is going to be the quarter of a circle. Okay, if we decide to proceed like this, let's just figure out what is y bounded by. Well, y is bounded by the plane xz, the xz plane, sorry. In the xz plane, y is 0, and above is bounded by the plane y is equal to z. And you see how easy it is, rather than bounding z between y and square root of 1 minus x squared. And the second part is the xz plane, so the projection of the solid onto the xz plane, which is this semicircle. You can choose now bound z between 0, the value z starts with 0 and ends with the square root, this is the equation of the circle, of 1 minus x squared. And finally, because it's a unit circle, x is between 0 and 1. So my triple integral becomes from 0 to 1 dx. Now the next one is dz, from 0 to square root of 1 minus x squared. And finally, y from 0 to z dy. And here I integrate the function. I integrate the function f. Any questions? Okay, if there are no questions, I'll do one more problem, and then I will the rest of the problems I'll do them. I'll shoot a video and I'll record the video and upload that one. In which case I'm gonna go very slowly, and I will also upload Frank's notes, where he covers many interesting problems, okay? And because he's going to write your test, this one, it's good to look at his notes. and the last test, and what else I wanted to say? Well, I don't know what else.
I have a small question just to be sure. If we want to find the volume, the function would be 1, like the function in the,
Yes,
in the triple
exactly.
integral?
Yep, yep, yeah. If you ask find the volume of the solid, then this function just becomes 1, right? This height in 4 dimension, you treat it as 1.
Okay, great, thanks.
Okay, so there is an example like that. Find the volume of the region common to the cylinders x squared plus y squared is equal to 1, and x squared plus z squared is equal to 1 in the first octant. Okay, so here I'm going to do a rough sketch and a little bit something a little bit more clear in the second sketch. So this is the cylinder x squared plus y squared is equal to 1, and the cylinder from the previous case x squared plus z squared is equal to 1. Okay. So what is going to be the intersection here? Obviously, it's going to be like this. Okay. Then it goes like this, and then something like that. It's not very easy to visualize it at the beginning, but let's just stick to only in the first octant. So we get, this is the projection onto the xz plane, right, of the cylinder x plus z is equal to 1. This is the projection of the cylinder x squared plus y squared is equal to 1 onto the xy plane, right? And then the cylinder goes like this, the cylinder goes like this, they meet here, and then you have this intersection here, this difficult part, right? So you have to evaluate the volume. The volume is just going to be the triple integral of 1 over this region, three-dimensional region E. And now, of course, it is up to you. How are you going to bound this? Okay. For example, what happens with the y value? So the y value goes from here, from 0 all the way to this, surface. But that surface is what? That surface is part of the cylinder. So y goes from 0 to square root of 1 minus x squared. Right? Now x or y, z. Doesn't really matter, so let's take z. Z goes from 0 to this surface right here. This surface is part of this cylinder, right? Of the cylinder x squared plus z squared is equal to 1, which means z is bounded between 0 and square root of 1 minus x squared. and then at the end, x goes from 0 to 1. So the volume is equal to the triple integral of 1. First I evaluate with respect to y, so y goes from 0 to square root of 1 minus x squared. Then with respect to z, from 0 to square root of 1 minus x squared. And finally, x goes from 0 to 1. In the x. Okay, so how much is this? The integral of 1 dy is just y, evaluated from 0 to 1 minus x squared, dz dx, which leaves us with the double integral you plug here square root of 1 minus x squared, so square root of 1 minus x squared minus 0 dz dx. Well, this expression here doesn't depend, doesn't depend on x whatsoever, on z whatsoever, so it's being treated as a constant, right? That's the integral from 0 to 1, square root of 1 minus x squared, times z, integral of 1, dz is just z, evaluated from 0 to square root of 1 minus x squared, dx, which is equal to the integral from 0 to 1, square root of 1 minus x squared, times square root of 1 minus x squared, dx. And now this is just Cal 1 example. Integral from 0 to 1, 1 minus x squared dx, which is x minus 1/3 x squared from 0 to 1. That's 1 minus 1/3. It's 2/3. So the volume of that intersections of those two cylinders is 1/3.
I know it doesn't really matter in the answer, but it's 1/3 x cubed.
Thanks. You're right about that. Thank you very much. Also, I'm exhausted by this third class today. Most probably you too. So guys, that's about it for today. As I said, I'm going to record a video on more problems like this and upload it. Next class we will do cylindrical coordinates. Okay, slightly more interesting because, and it is interesting because we're observing these forms, these solids as through cylindrical coordinates, so it's just more interesting and easier. Don't do that with your mouth. And then it's just spherical coordinates at the end, and there we're going to finish the semester. So next Monday, or let's say next Wednesday, we're definitely finished with the material. I'll have definitely one review class for the test, and at least one video where I'm going to cover many problems from the past finals. If you do these problems, you'll be more than ready for the test. As a matter of fact, the material for this test is is a short material, right? All you have to do is double and triple integrals. Are there any questions? No questions? Okay, well then, thank you very much. There is this guy who was waiting patiently to say bye. It's your turn, buddy.
Hello.
Hello. I say hi. Do you like calculus?
You got the coolest hair.
Yeah. Say thanks.
I agree.
And I don't have hair at all. So, that's why we're compatible, right? When the father doesn't have a hair, then he is like, okay, my son is going to have a long hair. All right, guys.
It's generations.
Yeah. Take care, guys. Stay healthy and see you on Friday. Bye bye,
Thanks,
everybody.
Eva.
Take care. Thanks.
Thank you.
Bye.